Hello everyone. Today we are going to be doing a video on linear algebra, of course, and today we are going to focus on row echelon form and Gaussian elimination, or an abbreviation for row echelon form would be REF. So I've prepared a system of three equations here, and today we are going to essentially solve for all of for the solutions for in three-dimensional space for this system of three equations using row echelon form and Gaussian elimination. So first of all, I'm just going to define row echelon form and Gaussian elimination. I'm just not going to start off with the problem right off the bat. I just want you to get a little bit of an visual intuition on what these are before we start. So if you remember, we have solved systems of equations in the past utilizing matrices, and this is essentially the same concept, but it's a quicker way of doing it, in my opinion. So how should I put this? Well, let's write this as you would normally do if you were wanting to invert a 3x3 matrix, because this can be written as -3. Remember writing down all the coefficients here. 6, -6, 7, and then x, y, z. You should, for further intuition on this subject, I would recommend watching my video on solving a system of three equations using matrices. And again, this is just a faster way of doing the same thing. And you've been really doing Gaussian elimination ever since you were doing Algebra 1. It's basically just solving for a system of equations. But it's just written in a different format. Let me finish this off. So this is obviously equivalent to this, right? You can multiply it out using scalar multiplication. So through Gaussian elimination in row echelon form, you will be able to rewrite this as in an augmented matrix. So we're going to essentially rewrite this 3x3 matrix. -1, 6, -6, 7, 3, -4, 4. You have this line here, and that symbolizes these values over here, -1, -7. So this is just a very common and important, crucial algorithm to solving for these types of equations on a high scale, on a computer, of course. So instead of doing all of this and multiplying this out, multiplying both sides by the inverse of this 3x3 matrix, basically you just put this in a very simple format in this augmented matrix, and it's much easier to compute that way, both for humans and for computers. So we have hidden the x's and y's and z's temporarily just to make this a little easier to do, to simplify. So essentially what you want to do is since we're focusing on Gaussian elimination, not Gauss-Jordan elimination, we'll probably cover that in future episodes. Not this one, though. For Gaussian elimination, row echelon form is defined as, if this is a square matrix, a row, this diagonal row of ones and zeros all around, zeros below that diagonal. So what we want to see in the end is, we can write this here. Something like this. This value doesn't matter. We don't care about these values at the moment. But what we care about is that there's a diagonal of ones there. We don't care about this. You do care about this upper part in Gauss-Jordan elimination, but not in Gaussian elimination or Gauss elimination, whatever you like to call it. So this is the format that we want to simplify this to. These can be any number, we're not worried about that section, but these sections have to be converted to zeros. These sections have to be converted to pivots or ones. So these even have a specific name because they're pivotal to your success in solving for the system of three equations. They're crucial because they are the coefficients of these terms here. So when you get them, you can just easily solve for that term since, well, that only applies to Gauss-Jordan elimination. But you would have to do a little more plugging in if you do Gauss elimination. Though you would have to plug in if you use Gauss-Jordan elimination because these would be zeros, so you would have the values here already. Okay, so now let's get started with doing this. So we're going to start off by getting this row to be a zero, to have a zero here, right? Because we want these three to be zeros. So let's do that real quick. Okay, so the way of doing this is, just to not confuse you guys, I'm going to write it out like this. So usually you would have to do some manipulation with the top rows here in order to fit this guy's opposite or opposite, inverse, and addition. So that if you add it to one of these terms here, it becomes zero. But we don't actually have to do any manipulating because we already have an opposite, this 3 opposite, so -3. So after adding these two rows evenly across, this one will become 0, but we're not actually changing these two rows. We're only changing this row. So this is allowed. So we're going to write this as now. Obviously these two rows stay the same. -1, 6, -6, 7, -7. But we don't know what this one is yet. Okay, so now let's add these rows, each term by each term. So this becomes 0. This term 2 plus -4, that's -2. -1 plus 4, that's 3. -1 plus -6. You can only add. While doing Gaussian and Gauss-Jordan elimination. That's you can multiply. You can add negative numbers to positive numbers, but you can't subtract rows from each other. So theoretically, you could just multiply this entire row by -1, but then add it to another matrix, and that's obviously allowed. So -1 plus -6, that's -7, right? So we have that going for us. Now let's simplify this further. Let's work on this top one here. So now in order to get its opposite, we need to multiply this entire row by 2, right? We want to get a -6 up here, so when we add it to this row, we can get a 0 up here. So let's write that out. So this will stay the same still. And basically what we've computed here on the first run here, I'm not talking about this one yet, is we have added row 1 to row 3, and the changes are directed towards row 3, not row 1. So we can write it like that just to not confuse, but I'm not going to write it like that throughout the video, just so that, because I think it's relatively simple and it doesn't have to be written out if it's spoken orally. So now we don't have to change this row, so we might as well just write it down here. This does take up a lot of space, as you can see. So what's -6? What's -6 plus 6? Well, that's just 0, right? That's what we're trying to do. Oh, sorry, I wrote this down from here, not from there. Well, not from there. Oh, I messed it up a little bit. It's fine. We're not focusing on that row anyway. This is 0. My bad. Okay, so what's this multiplied by 2, right? 4 plus negative 6. That is just negative 2, right? And then what is negative 2 plus 7, right? So you're just multiplying this by 2. That's just 5. And negative 1 plus multiplied by 2, that's 2. That's negative 2. Negative 2 minus 7, or negative 2 plus negative 7, obviously, which is equivalent to that. That's just negative 9. Okay, so let's rewrite this quickly because this looks horrible. We should probably switch to a new page. I don't want to fit in all of these matrices, so I'll write it. So now I'll show you what I'm going to do next. So now for a final 0, we want to convert this negative 2 into a 0. Now what we're going to do is, I'm going to write this out for the last matrix because why not? We have open room here. So what I'm going to do is I'm going to subtract, I'm going to add row 2 to row 3, and the changes is directed towards row 3. Okay? Okay, so I'm just going to rewrite this. So what I'm going to do is since these are 2 negatives, I'm going to multiply this entire row by a negative. So all of these signs are altered. So that should, and that obviously doesn't change the answer itself. So I'm going to write this out. This stays the same. Negative 1. This guy still stays the same. Okay, and finally, we're going to have to rewrite this part here. Hold on, let me just make sure that I have written this in terms of the 0 here. So I have multiplied this by 2, right? Multiplied by 2. Yeah, I wrote that correctly, just making sure so I don't make any silly mistake. Silly mistakes are never nice. So now what we're going to do is we're going to multiply this entire row, like I said, by negative 1. So that this becomes a positive 2, which is the opposite of 2, or the opposite of negative 2. So we can add the totals. So we still have a 0, right? Because 0 plus 0 is just 0. So this becomes negative, so this becomes a 0. So then we have, oh, I really made a mistake by writing this badly. Oh, I see what I've done. So I've really confused myself. So this is negative 2 and 3, right? Negative 2 and 3. So, well, negative 2 is, we don't have to worry about that. But this term is now 3. So 3, I have got myself into a bit of a problem. So negative 5 plus 3, that's just negative 2, right? And then that's negative 7. So 9 minus 7, that's just 2. Okay, and now we're ready to plug this in and write it as a system of 3 equations again. And let's see if that allows us to solve for x, z, and y. And it will. So let's write what do we have here now. So 0x and 0y and 0z, they just simplified to 0. So these zeros are just, those terms have been converted to 0, and as a result, they're not there anymore. So the top row is just going to be the same as it was a while ago, beginning. And I'm just writing the corresponding coefficients to what would have been here. right? And that should be equivalent to our equation here, and it is. And 0, so this negative 2y, right, because x is gone, plus 5x equals negative 9. And finally, oh, by the way, I should probably enlighten you about row echelon form, so I'm just going to this. Okay, so row echelon form calls for pivots in this diagonal here, or ones. So this entire diagonal has to consist of ones. So technically, you don't have to complete it to full row echelon form, but it would be recommended for at least the first few terms. So if you multiply both sides of this by negative 1/2, right? We want to convert this to 1. Then that becomes 1 is equal to negative 1. So now we know that z is equal to negative 1, and if we solve it here as well, z is also in this case equal to negative 1. So theoretically, if we just convert all of these accordingly, like we've done with this, then we'll receive the same answers as we do it here. So I'm just telling you right now, just so you don't get confused, what I'm doing here right now is not full row echelon form. Full row echelon form would be where all of these are ones, like I said, or pivots, as I usually say, and how it's usually said. But I've only done this portion where these are zeros. So in my opinion, it's more simple to just convert these to zeros and then plug in the values accordingly, rather than converting these to ones, because obviously you would get fractions, improper fractions. That can get a little tedious. So I don't want to make that I don't want to make that confusing, because it's really simple and that'll confuse everyone. So let me get started. So let's continue. So we found that this is the last equation. Negative 2 multiplied by z is equal to 2. You divide both sides by negative 2, as you would usually do if you solve for variables, and you receive negative 1. So now we know that z is equal to negative 1. Now, sorry, this is an x, this is z, right, because it's the last term here. So that's negative 2y plus 5z. Okay, so now let's just plug in z here. So that just converts this to negative 5, and we can solve for y accordingly. So negative 2y plus negative 5 is equal to negative 9. Negative 2y is equal to, right, negative 5, so you add 5 on both sides, is equal to negative 4, divide both sides by negative 2. I'm writing this out just so you can easily see what I'm doing. Y is equal to 2. So now we can plug both of these values into this final equation. So negative 3x, we don't know what x is yet, plus 2 times 2, right? Y is equal to 2, minus 1 times negative 1, because we found out that z is equal to negative 1, and that's all equal to negative 1. Okay, so let's simplify. Negative 3x plus 4, right? Plus 1 is equal to negative 1. Negative 3x plus 5 is equal to negative 1. Hold on. So negative 3x plus, whoops. So you would minus on both sides, so is equal to negative 6, and then divide both sides by negative 3. That's x is equal to 2. So now we've just found out that we've found the solution for the system of 3 equations. The value of x, the value of y, and the value of z. So at that point in 3-dimensional space, all of those planes, obviously. I'll give you a visual representation of graphing things in 3 dimensions on paper. Kind of like graphing 4 dimensions in real life. Anyway, let's just write this out as a matrix, as a column vector. So at these points where this is equal to x, this is equal to y, and this is equal to z, at those points in 3-dimensional space is where all of 3 of these planes will intersect. Okay, so thank you everyone for watching. Hope you guys enjoyed, and next episode we are going to work on reduced row echelon form, or Gauss-Jordan elimination. So hope you guys enjoyed again, and see you in the next video. Goodbye. Oh, it's blurry.